random positions and move in random directions. But one can also ask the question, what happens if you keep on pressing this system to infinite pressures, to the densest packing that these systems can appear in? And this question was already asked by Sir Walter Rayleigh, a sailor in the UK. He asked this question to Kepler, and Kepler conjectured in 1611 that the stacking of hexagonal planes, as in face-center-cubic crystals or hexagonal close-packed crystals, has the maximum packing fraction. And the maximum packing fraction is 74% of the space is filled by these spheres. And one can see the cannonballs at the picture here below. It's just a stacking of hexagonal planes. And it took the mathematicians more than 4 centuries to come up with a proof. Thomas Hills came up with a proof by exhaustion in 1998. The referees costed more than 5 years to analyze this proof. And in the end, they concluded that they were 99% certain of this proof. And they accepted Kepler's conjecture as a theorem by then. And Thomas Hills announced in 2014 a formal proof, which was finally accepted in 2017. So only a few years ago, it was a formal proof of the best packing of spheres was accepted. However, already in 1957, computer simulation showed that there's a spontaneous crystallization of hard spheres. So if you compress hard spheres above a packing fraction of 0.55, it spontaneously organized themselves into a face-center cubic crystal phase. And this was work by Alden Wainwright and Wood Jacobson. It took the experimentalists more than 30 years to synthesize colloidal particles that are perfectly spherical, well characterized, and that the sizes were such that they were sufficiently monodispersed, and to find also this freezing transition in colloidal hard spheres. And this work was work by Pusey and Van Meeken, who published this in 1987. In fact, opals, the beautiful colors of these gemstones, are in fact due to the stacking of silica spheres in these ordered arrays. And later on also, these colloidal crystals were found in other systems, silica spheres, cobalt nanocrystals, iron nanoparticles, and so on. So can we also understand this phase transition? For that, we have to go back to thermodynamics. And phase transition only occurs if this results into a lower Helmholtz free energy. And the Helmholtz free energy is just the potential energy, U minus T, the temperature, times the S, the entropy, for a fixed number of particles, volume V, and temperature T. And because only non-overlapping configurations contribute to the configurational integral or the partition function, the potential energy is always 0 for these hard particle systems. And so a phase transition can only occur if this results into an increase in the entropy. And if you use our intuitive notion that entropy is a measure for disorder, one would say a fluid is much more disordered and has a higher entropy, whereas a crystal is more ordered or looks more ordered and has a lower entropy. So intuitively, you would never expect to have a spontaneous transition from a disorder to an ordered transition. But if you go back to the more precise definition of entropy that was introduced by Ludwig Boltzmann, and it was even engraved in his grave tomb, S equals K log W, with W the number of configuration, one can easily see that if you make a schematic picture of a fluid phase at sufficient high density and of a solid phase also at the same density, one can immediately see that in the fluid phase, all the particles which are random are completely jammed with respect to each other, so they can't move anymore, whereas in the solid phase, where all the particles are located at their lattice position, all the particles can still wiggle around their lattice position, and the wiggling room means more configurations, and so the entropy is actually higher for all these crystal structures. However, all these crystal structures look all more ordered than in the fluid phase. So there are many more configurations, but all these configurations are more ordered. And so one can obtain order through disorder, and entropy strikes back. So to increase the structures that one can make, one can also look at mixtures, big spheres and small spheres, determined by a size ratio Q, which is the diameter ratio of the two spheres. If we consider, for instance, a size ratio of about a half, so the small spheres are twice as small as the big spheres, then one can get extremely exotic crystal phases. One of the most exotic crystal phases is the AB13 crystal phase, where the big spheres are sitting onto a simple cubic lattice, but at a distance so far apart that an icosahedral cluster of small spheres fits perfectly in between this simple cubic crystal structure. And these icosahedral clusters are rotated by 90 degrees with respect to their neighboring clusters. Another crystal is just the AB2 crystal. It's stacking of hexagonal planes of big spheres, and then a Kagome lattice of small spheres, and then a hexagonal layer of big spheres. And it's an alternating sequence of big spheres, small spheres, big spheres, small spheres. And these crystal structures have been obtained in the bigger colloidal particles, but also in the nanocrystal suspensions. And again, all these very exotic crystal structures are purely entropy driven. So it's only entropy, no weird interactions, that drives these crystallizations or the self-assembly into these highly exotic structures. Another crystal structure that is very interesting are the so-called lattice phases. This is for a size ratio of about 0.7, 0.8. There are three types of lattice phases. The magnesium copper 2 phase, which is actually the big spheres form a dimer, and these dimers are stacked into an ABC fashion. Whereas in the magnesium zinc phase, which is the most stable lattice phase, the stacking is AB for the dimer lattice. And then there's a more exotic stacking in the magnesium nickel phase, where the stacking is ABAC, ABAC. And so the most interesting phase is actually the magnesium copper phase, which is actually not the most stable phase, but the magnesium copper phase consists actually of a diamond lattice of the big spheres and a pyroclase lattice of the small spheres. And so if you can self-assemble using colloidal hard spheres, this lattice phase, the magnesium copper phase, and one can burn away, for instance, one of these pieces, one ends up with a diamond structure or with the pyroclase structure, and both the diamond and the pyroclase structure exhibit a photonic band gap invisible, as can be shown in this band diagram. And so this would be a very interesting way to produce a photonic band gap structure. However, these lattice phases so far have only been seen in nanoparticle suspensions and never for the bigger colloidal suspensions, which are relevant if you want to make a photonic band gap structure. So this is the packing of spheres, but also packing of mixtures of spheres. I only discuss the densest packings and the densest periodic packings, not random packings. One can also consider other particle shapes. So the chemists, due to many advances in the chemical synthesis, one can make all kinds of particle shapes nowadays. And the first question that we addressed several years ago is, can we predict these self-assembled structures for odd-shaped particles? Can we predict the densest packings for these odd-shaped particles? And because this is a notorious difficult question that was already raised by many people in the literature, we decided to work on this in the context of these colloidal particles. And we followed different routes, also genetic algorithms, evolutionary algorithms, but in the end we came up with an extremely simple method, which was just plain Monte Carlo simulations using a very small number of particles in the simulation box. So we basically simulated only the unit cell. The shape of the simulation box could vary, and we used periodic boundary conditions because we were interested in periodic structures and periodic crystal structures. And then by just using the isobaric thermal ensemble, so we fixed the number of particles and the pressure of the system, we could slowly increase the pressure to find the densest packing, or we could slowly decrease the temperature in order to find the ground state structures. And later on, we combined it with a triangular tessellation method and a very fast triangular interference detection method in order to describe the surface of any particle shape. And so here are two examples: it's a system of big spheres and small spheres, also a system of hard tetrahedra. One can clearly see that the simulation box is floppy, it varies all the time. And this is very useful because you can scan over many different structures by just using this fluctuating simulation box. And by just using a simulated annealing technique where we increase the pressure in steps, we were able to find the densest packings. So this is for instance, the densest packings of a binary hard sphere mixture, but also of a densest packing of tetrahedra. We also looked, for instance, at truncated tetrahedra. They can nearly fill all of space. This was demonstrated by Salto Creto, who showed that the densest packing of these truncated tetrahedra is 207 over 208. So almost 99.5192% of space is filled by these truncated tetrahedra. These truncated tetrahedra form a dimer. I will come back later on to these dimer lattices again. These dimers are centrosymmetric compounds, and these dimers, these centrosymmetric compounds, will just self-assemble onto a Bravais lattice. One can also look at other truncations, so one can start with straight tetrahedra and then truncate the corners slowly of these tetrahedra. This was done by Michael Engel and Sharon Glotzer, and one can see that also the other truncated tetrahedra fill space, all of space nearly. Another particle shape we've looked at is that of hard cubes. They form a simple cubic lattice, and this fills 100% of the space. But if you look, for instance, at the colloidal particles, then these colloidal particles, which are made using hematite cubes and then growing silica around it, they are slightly rounded. And that's why we also decided to look at rounded cubes, where we could go from just straight cubes all the way down to spheres via rounded cubes, and then we could go to rounded octahedra to straight octahedra. And these shapes are just parameterized by this expression here. And so for this system, we also calculated the phase diagram. We first use our crystal structure prediction method to find the densest packings. They are denoted here by this solid black line here. And one can clearly see that the spheres are the worst packing shapes if we consider it with respect to the cubes in the octahedra. And this is well known in literature. So this is the phase diagram. On the y-axis, we show the packing fraction, and then on the x-axis is the shape parameter. So it goes from cubes via spheres down to octahedra. For very low packing fraction, we find a disordered fluid phase. And then if we increase the packing fraction, it can form a plastic FCC crystal phase or a plastic BCC phase. These plastic crystal phases are just the FCC or the BCC phase, but the particles can rotate freely while sitting on these lattice positions. In the case of cubes, we find a simple cubic phase. If we make them rounder, it transforms into a deformed simple cubic phase. And then on the octahedral side, there's the Minkowski lattice, and it is basically a deformed BCC phase. So these are the shapes. So these are the different packings for spheres, mixtures of spheres and different shapes. We can also increase the diversity of crystal structures by using just confinement. And for instance, if we start with a face-centered cubic crystal of spheres, one can also ask the question what happens if you confine these spheres into a planar slit. So if the slit consists of two planar hard walls and you confine the spheres in between. And this question was already addressed by Piransky and Ponsou, who did both experiments and, on these colloidal spheres in between two glass platelets. And the angle between these glass platelets is given by this angle, and by just using this angle, they were able to probe all possible plate separations at once. And what they found was that there's an alternating sequence of triangular square, triangular square, triangular square layers. So the best packing in the lateral plane you obtain with a triangular lattice, an hexagonal layer. But if you increase the plate separation slightly, then the density packing in the transverse direction is just a stacking of two square layers. And so that's the reason why it alternates from triangle layers to square lattices to square triangle layers to square lattices. Matthias Smith and Hartmut Neuer found that there were also intermediate structures like a buckling phase and a rhombic phase, and we revised this phase diagram by just using free energy calculation, and we found many more intermediate structures as well. So this buckling phase, the rhombic phase, but also a whole zoo of prism phases. So one can, for instance, take a path along these best packings. So they are these paths here. The gray region is just beyond the maximum packing, and just along these lines are the best packings for that system at that plate separation. So if we take, for instance, the green path where we start with two square layers, we will, if we decrease the plate separation, we will transform into a buckling state, and then it will form one single triangular layer. And this is shown, for instance, here. I don't know. Yeah. It started with two square layers, and then it forms a buckling phase, and then in the end, all the spheres are in just a single triangular layer. One can also take an opposite path, so we start with two square layers and then increase slightly the plate separation so that we take a path at these maximum packings. And there's a rhombic phase, and then it goes towards two triangular layers. And that's shown here. It starts to buckle, and then in the end, it forms two triangular layers. And all these crystal structures or structures were also found experimentally in polystyrene spheres, but also in charged spheres. So one can also look at these prism phases. There's a whole zoo of these prism phases. They're denoted by a number, which is the number of layers in these prisms. And we can see if you start with these prisms, there are these twinning planes in between the prisms. We can increase the plate separation, and then it goes to 5 square layers. So there's a whole zoo. Also these prism phases have been found in experiments but in the group of Thomas Palmberg. One can also, of course, put spheres into a cylinder. There's beautiful work done by Pickett and Okuyama, but also by Adil here. One can also look at packings of spheres in a tiny spheres, such that one can obtain small clusters of microspheres. These are so-called colloidal molecules, which can be used in self-assembly experiments. And one can also adhere particles at the interface. These are, for instance, systems of oil and water, and the particles like to be at the interface, or they adsorb to the interface. And one can see that one can obtain whole lines of disclinations, which are also called scars or pleats in crystals on curved surfaces. What we would like to do here is just to make bigger particles. And so if we start with, for instance, atoms, and we self-assemble them into a crystal, we obtain a so-called nanocrystal particle. If we use these nanocrystals in a self-assembly experiment, we can make all kinds of packings. But if we perform the self-assembly in the spherical confinement of, for instance, an emulsion droplet, we can make a bigger particle out of it. And we call these so-called supraparticles. So these bigger particles can then be used into a next self-assembly experiment to make even bigger structures. And so this is more or less the motto that we use in our group. If something looks very nice, a nice particle shape or a nice structure, just put it in a sphere and you can make a supraparticle which can be used into a next self-assembly experiment. And so this is what we started several years ago. We used an emulsion. We can confine the nanoparticles into these emulsion droplets. Depending on the size of these emulsion droplets, there are different numbers of particles that we can confine into these emulsion droplets. Here we can see that we have 130,000 particles, or smaller droplets contained 8,900 particles. And we analyze all these structures using an electron microscope to analyze what kind of structures we get out. And so we slowly evaporate the solvent out of these emulsion droplets in such a way that we get just a cluster out of it. And what we found, to our surprise, was that up to 1,000 particles, we find very beautiful icosahedral clusters. If we go to bigger clusters, up to 10,000 particles, we find a rhombicosidecahedral cluster. And if we go to millions of particles, we go into the limit of bulk, and we find just a single FCC cluster. And one can see very nicely these ledges at the outside of this single FCC crystal. So these icosahedral clusters are very intriguing. They consist of 20 slightly distorted FCC tetrahedral domains. These pi slices are all pointing inwards. They all meet in the center of this icosahedral cluster. At the outside, you will find five-fold symmetry at the 12 vertices. And so there are 30 edges and 13 twinning planes inside this icosahedral cluster. If the particle is bigger, so it likes to grow further, then you will have all these tetrahedral domains, 20 of them. An ATP plane is grown on top of these tetrahedral domains, and then another FCC domain is formed on top of these tetrahedral domains. And these triangular wedges are just filled with another FCC unit. And then the outside looks as follows. There's this five-fold symmetry in the middle. There are these 100 planes, which are, and then there are these 111 triangular facets also at the outside. One can also do the same trick with bigger colloids. These are 1.3 micron sized silica colloids. One can clearly see the colloidal particles in these emulsion droplets, and by just evaporating slowly the solvent out of these emulsion droplets, one can increase the density in such a way that it self-assembles into these beautiful icosahedral structures, or rhombicosidecahedral structures, or these single FCC. So also for the bigger colloids, we find all these beautiful structures just by putting spheres inside a sphere. So in simulations, we can also look at the crystallization mechanism. One can see immediately that there's a strong layering of the spheres at the surface. The spheres try to self-assemble these tetrahedral domains. If they grow too big, they melt again. If they are not big enough, they grow further. And then in the end, you get this beautiful icosahedral cluster just by just putting spheres into a sphere. And this is completely entropy driven. So I find this awesome that it just self-assembles into this icosahedral structure and knows how to assemble 20 of these tetrahedral wedges. So here here we calculated, for instance, the fraction of crystalline particles in the surface layer, and then the first layer, the second layer, and the third layer. This is as a function of packing fraction, but because we compress the system slowly, because the solvent evaporates out of these emulsion droplets, the packing fraction can also be seen as time. So the surface starts to crystallize, then the first layer, then the second layer, then the third layer. Then the interior starts to crystallize. If the interior starts to crystallize, the outer layers melt again. But then if this HCP plane is grown on top of these tetrahedral domains, then the outer layers crystallize again. We also calculated free energies. So for all these icosahedral clusters that consist of highly strained FCC domains, 20 of them, and then the 13 twinning planes, they do have a lower free energy than the FCC cluster because of the spherical confinement, whereas the FCC phase is actually the thermodynamically stable phase in the bulk limits. And more free energies were calculated by Michael Engel, who showed that there are really magic numbers. So if you are at a magic number that really fits perfectly inside the sphere, you find the free energy minimum. And they did beautiful work on calculating the free energies and looking at the structures of these icosahedral and rhomicosahedral clusters. One can also look at superballs. That's why I discussed the superballs earlier. One can start, for instance, with superballs that are very close to cubes. These are the experiments done by Da Wang. I think he's in the audience here. There's a block of simple cubic crystal in the middle, but then all the cubes also like to align the surface of this spherical confinement. And that can be seen also here in the simulations. There's a big block of simple cubic crystal in the middle, but also at the outside, the cubes really like to align along these spherical confinements. And if you look at the outside, we find 8 of these topological defects with a winding number of pi/2, and it satisfies the Poincaré-Hopf theorem. We can also look at superballs that are closer to spheres. Then we find immediately that the clusters show this 5-fold symmetry. If we compare that then with the simulations, we clearly see a very strong resemblance between experiments and simulation. And for cubes that are closer to spheres, you will find these FCC domains back and these tetrahedral domains. And so we also analyze this as a function of the roundedness or the asphericity of the cubes. So here we start with spheres and then we go towards the cubes. And we find if we just calculate the fraction of FCC or HCP or simple cubic, we see that the cubes, they form almost 100% simple cubic crystal structures, whereas the spheres, they form 100% FCC or hexagonal close-packed structures. And in the middle, it crosses between FCC to cubic. One can also look at other shapes, short rods. One can even make smectic layers inside the spherical confinement. One can also look at platelets. These are diamond-shaped platelets. They form nice columns, and so these superparticles are completely filled with these columns of these platelet particles, which can also be shown here. One can also look at circular platelets. For that, we find that they form also these stacks of or columns of platelets, but we also found a very nice twist or Caro arrangements of all these columns. And this is very similar to if you have filaments and you use a geometric frustration due to confinement, you will find that they form Caro structures. And then last but not least, we can also look at binary systems, binary mixtures of hard spheres in spherical confinement. We used the nanoparticle, the lead selenide and the cadmium selenide nanocrystals. They form in the bulk the most stable magnesium zinc lava phase. If we put them in confinement, we find again this very beautiful five-fold symmetry, both in experiments and in simulations. In simulation, we could also analyze the crystallization mechanisms. Here we find that the crystallization really starts at the off-center position in the spherical confinement, and then from there on, it tries to grow these 20 tetrahedral domains. So it's a completely different crystallization mechanism than in the case of just pure hard spheres, where it started to grow from the outside to the inside. What is very interesting here is that if you look at the tetrahedral domains, they consist now of magnesium copper phase instead of the magnesium zinc phase, which was the most stable structure in the bulk phase. And to understand why the crystal structure changed from magnesium zinc into magnesium copper phase, we should have a look at the subunit of these Navier phases. So these Navier phases consist of big spheres and small spheres. The big sphere is in the middle of a truncated tetrahedron, so that's why I discussed the truncated tetrahedron before. The small spheres are at the vertices of this truncated tetrahedron. There are 12 of them surrounding this big sphere in the middle. One can easily make five-fold symmetry using these truncated tetrahedron. If we use 20 of them, we can make an icosahedral cluster, which is also called the Bergman clusters. And the Bergman clusters are already known that they play a major role in the formation of these icosahedral quasicrystals. So these Bergman clusters, they consist of a single sphere in the center. Then there's an icosahedral layer of 12 spheres around it. Then there's a second layer of 20 layers in a dodecahedral fashion. Then there's a 12 spheres around it in an icosahedral fashion. And then around that, there's 60 particles in a truncated icosahedral fashion, which is basically the soccer ball. So these subunits of the lava phases, this is the truncated tetrahedron. One can immediately make these icosahedral clusters. These truncated tetrahedron also like to form dimer lattices. This was already shown in only covers of these two journals. And these dimers of truncated tetrahedra are also called the free-valve polyhedra. In the case, and one can stack these free-half polyhedra into a dimer lattice, which is basically a Bravais lattice. In the case of these lava phases, these free-half polyhedra are stacked into an ABC fashion in the case of the magnesium copper phase, as shown here. In the magnesium zinc phase, they are stacked in the AB fashion. So here we've printed 3D printed many of these truncated tetrahedra just to understand these crystal structures. In the magnesium zinc phase, it's an AB stacking, so it's a sort of zigzag stacking. In the case of the magnesium nickel phase, it is an even weirder zigzag stacking in an AB-AC fashion. And so if you want to grow bigger tetrahedral domains, this is only possible if you have a magnesium copper phase. And so that's the reason why it turns from the more stable magnesium zinc phase in the bulk towards a magnesium copper phase when you confine these particles inside a bigger sphere. So we can also peel off all these layers out of these clusters, start with the center of this cluster. There's a single sphere in the cluster, a small sphere in the cluster. If we then add all these layers again around the single sphere in the center, we find an icosahedral shell of 12 small spheres around it. Then we find a dodecahedral shell of 20 big spheres around it. We then find an icosahedral shell of 12 small spheres around that center. This then a truncated icosahedral of 60 small spheres. This is basically the Bergman cluster. So we have one subunit of the Navier phase now self-assembled into this icosahedral cluster. But we can now also go further and we found that there's a dodecahedral shell of 20 big spheres around it, then an icosahedral shell of 12 small spheres, an icosahedral shell of 30 small spheres, and then a rhombicosahedral shell of 60 big spheres around it. And one can still see these pentaconical symmetries at the outside of this cluster. One can also zoom into these, let's say pentaconical tubes. And if you look at that, we find that these pentaconical tubes, there are 12 of them because it's the icosahedral cluster with 12 of these vertices. They are alternating sequences of big spheres, small spheres, big spheres, small spheres. So just putting big spheres and small spheres in a big sphere, it self-assembles spontaneously, purely entropy driven into this very beautiful structure where it really forms all these layers of icosahedral, dodecahedral, etc. layers around a central sphere. And then with all these pentaconical tubes, 12 of them that basically spans up all these magnesium copper 2 wedges. So I find this really awesome that it really self-assembles this way, both in experiments and in simulations. So this basically brings me to my conclusions. One can structure matter over multiple length scales using hierarchical self-assembly of colloids. One can start with atoms and self-assemble them into a nanocrystal such that one obtains a crystal of atoms. One can perform the self-assembly of these nanocrystals in a spherical confinement of an emulsion droplet such that one gets a bigger cluster. One can then self-assemble these supraparticles again into a bigger structure such that one really have hierarchical self-assembly. And so the take-home message is that one can obtain many different packings, many different nanostructures, depending on the number of components that you use, the particle shape, and the confinement. And one can even tune the particle interactions if you want to. So all the systems that I showed here are all hard particle systems, which are all purely entropy driven. And with that, I would also like to acknowledge the people. All the experimental work was done by Bart de Nijs and Dao Wang and Ernest van der Wee, under the supervision of Alfons van Bladeren. There's a whole team of simulators that contributed to this work. Tunisia Dasgupta, Gabriele Colli, Nick Tasios, Frank Smallenberg, and Simone Dussi. And then we also collaborated with Sarah Bowles for the electron microscopy and Chris Murray for the particle synthesis. And with that, I would like to thank you for your attention.
Thank you very much for your talk,